All right, in this video, I'd like to start you off on your homework. So I have the relativity problem set in front of me, and I'd like to talk through numbers 1, 2, and 3 together, and then I think you'll have enough of a background that you'll be able to do the rest of them yourself. So we've been talking about traveling in a spaceship like near the speed of light. So I was curious about how fast do we currently know how to go? What is the fastest that we have gone? Obviously we've taken subatomic particles and we have moved them very close to the speed of light. But what about a person? Like if you wanted to get into an airplane, what do our fastest airplanes? How fast can they go? So I Googled it. So the fastest airplane is called the X-15. And it's the fastest manned aircraft. So obviously that means a person or a pilot is in that. Its maximum speed was 4,474 miles per hour. So about 4,000 miles per hour, which is about equal to 2,000 meters per second. So we're going to pretend that we could take this fastest airplane and we are going to fly it to our nearest galaxy, Alpha Centauri, which is this many meters away. So if we could take this plane, how long in years would it take us to reach this galaxy? So I'm just going to use a very simple constant velocity equation. So velocity is distance over time, because in the special theory of relativity topic, we are limited to moving at a constant velocity. Let me see if I can get this light a little bit out of our way. It might help. Maybe not. Okay, so we are going to take this X-15, which moves at a velocity of 2,000 meters per second, and we're going to Alpha Centauri, which is 4.07 times 10 to the 16 meters away. And the question is, how long is it going to take us to get there? So I just need to solve this for t. All right, let's see if this will project. So I'm going to put in my distance, 4.07 to the 16, and we'll divide by 2,000. All right, so that's how many seconds it would take. So 2.035 times 10 to the 13 seconds. But we have to turn that into years. So let's just pop into our conversion menu here. And so this is time, this is seconds, this is years. And that's going to take a lot of years, 644,000 some years. So let's write that down. 644,866 years. I won't write the decimal places because they're insignificant anyways. All right, but the point of that is, even if we took our fastest airplane that we currently have, we are so going to die someplace along this trip, okay, because it's going to take us way, way, way too long to get there. So we're stuck here in our own galaxy until we learn to go faster. So in number 2, we're going to pretend that in the future we have now built an airplane that does go faster, or a spaceship, and this spaceship is going to travel at a velocity near the speed of light, so 2.999. So I'm going to write that down, 2.999 times 10 to the 8th. I just got to take this fast spaceship and I'm going to head to Alpha Centauri again. And the question is, how long will it take? So this time I have 4.07 to the 16, but we're going faster. So we're divided by 2.999E8, and it's going to take me this many seconds to get there. This many seconds, and let's convert that into years. It's going to take me 4.3 years to get there. Time equals 4.3 years. All right, so if we could build a rocket ship that went near the speed of light, this is a doable feat. So I'd be willing to spend 4.3 years in this spaceship to go visit Alpha Centauri. So let's say your plan is to, or an astronaut's plan is to spend 4.3 years in the spaceship, go to Alpha Centauri, take some pictures, and then bring them back to the Earth. So that's what we're doing on number 3. So the issue is, as soon as I say to myself that I am traveling at relativistic speeds such as this, then I have to know that relativity is going to take place and there's going to be changes that happen in terms of time, mass, and length. So I'm going to use relativistic time here, kind of talking to myself. So if I actually took this trip, and if I was in the spaceship for 4.3 years, the question is how much time would be passing on Earth? So let's figure that out for a minute. Whoops, that's a 9, there's an 8. I really messed that up. Times 10 to the 8th, and then I got to square that mess. And on the bottom, we have 3 times 10 to the 8th, and we have to square that. So every calculator kind of has its own little keystroking, and so this is an old calculator. I like the conversion menu, but I got to work my hardest on the keystroking here. So I'm going to go 2.999 E8. Then I'm going to square that. Then I'm going to divide it by 3E8. I'm going to square that. Then I'm going to go 1 minus that. Then I'm going to square root that. Then I'm going to go 4.3 divided by that. And I find out that on Earth, 166.55 years have passed. So maybe my goal was to spend 4.3 years in the spaceship. I take some pictures, and then I come back. It takes me another 4.3 years. So really, I have been gone now, technically 8.6 years by the time I come back. And on Earth, on my way there, 166.55 years took place. And then on my way back, another 166, so I'll just times 2. And so on Earth, 333.1 years have taken place. And so, obviously, when you get back with your pictures on a very doable trip, there's nobody that you know left on Earth to show your pictures to. Well, there might be people, but they don't know you. And if you try to explain that, well, you know, I used to live here on Earth and I just took this trip and I just brought some pictures back, they might not believe you and they might not fall for that. All right, so this was an example of, obviously, time dilation. So as you continue on the homework, it's just reading the problem, knowing what equation to choose, knowing where to put the variables, and practice solving for different variables. And so today, the A students spent a little bit of their time in class working on the problem set. I don't know how far they got. They didn't finish. But I'm hoping that you can get started and that you can have the problem set completed by Sunday night so that on Monday we could turn in the problem set and be able to go forward. Okay, good luck.